Every single moment of our lives is intricately woven with the silent, invisible dance of atoms. With each breath we take, with every touch we feel, we are continuously interacting with these fundamental particles. Yet despite their omnipresence, the true nature of atoms remains elusive, wrapped in layers of mystery. In this journey, we will attempt to unlock the enigma of the atomic world, where every interaction, every bond, and every form of matter begins. Here, we will search for the answers to the deepest questions about the building blocks of our universe, the forces that shape the world around us, and the forces that bind everything together. At its core, the atom is the smallest indivisible unit of ordinary matter that composes all chemical elements. Every substance, be it solid, liquid, gas, or plasma, consists of these incredibly tiny particles, either in a neutral state or as ions. But what exactly defines an atom? At the center of each atom lies the nucleus, a dense core composed of two primary types of particles, protons and neutrons. The protons, each carrying a positive electrical charge, are the nucleus' most energetic inhabitants. Meanwhile, the neutrons are neutral particles, lacking any charge, yet playing a vital role in the atom's stability. Surrounding this tightly packed nucleus are electrons, minuscule particles that are infinitely lighter than protons or neutrons. These electrons orbit the nucleus in distinct energy levels known as electron shells. Despite their negative charge, electrons do not follow simple, fixed paths. Instead, they exist in regions called orbitals, cloud-like zones where their exact position is governed by probabilities. It is within these orbitals that electrons facilitate the critical process of chemical bonding, where atoms exchange or share electrons to achieve a more stable configuration. This process forms the foundation for the creation of molecules and materials. But what is truly remarkable about atoms is the staggering amount of empty space within them. In fact, if you were to scale up the size of an atom to the proportions of a sports stadium, the nucleus would be as small as a peanut sitting at the center of the field, with electrons whizzing around the stands like tiny energetic flies. The vast emptiness between the nucleus and the electrons, despite seeming counterintuitive, actually defines the way matter behaves at both the microscopic and macroscopic levels. The identity of any given element is determined by the number of protons it contains within its nucleus, referred to as its atomic number. This number dictates not only the element's properties, but also its interactions with other elements. However, the story of the atom doesn't end with this simple model of protons, neutrons, and electrons. As scientific knowledge has evolved, so too has our understanding of atoms. We now recognize that the atom's true nature goes far beyond this basic description, offering an entirely new realm of possibilities. The quantum mechanical model of the atom, the one we work with today, presents a much more complex and fascinating perspective. In this quantum world, electrons do not move in neat, predictable orbits as once thought. Rather, they are described by probability waves existing in regions of space known as orbitals, with no precise fixed locations. This understanding has revolutionized our ability to predict the behavior of atoms, not just in simple chemical reactions, but also in the design of cutting-edge materials and technologies, ranging from microelectronics to life-saving medical devices. But quantum mechanics has also unveiled another layer of complexity. The atomic number, which defines the element, remains constant, yet atoms of the same element can vary in mass. These variations, known as isotopes, occur when an atom has the same number of protons but a different number of neutrons. This difference can result in distinct physical properties. It's these variations that help explain why some elements are stable while others are radioactive. The concept of isotopes has profound implications, from dating ancient fossils and rocks to powering nuclear reactors. The quest to understand atoms is not a modern phenomenon. The idea of the atom dates back to ancient times, when Greek philosophers first proposed the concept. Around the 5th century BCE, the philosopher Democritus introduced the radical idea that all matter is made up of tiny, indestructible particles he called atomos, meaning uncuttable. Democritus's insights, though based more on speculation than empirical evidence, suggested that the changes we see in matter are not due to changes in the fundamental substances themselves, but rather in how these substances are arranged and combined. His theory proposed that atoms could take different shapes and sizes, and it was their interactions that determined the properties of the materials they formed. Though Democritus's ideas were ahead of their time, they remained largely theoretical for centuries. It wasn't until the early 19th century when English chemist John Dalton revived and refined the concept based on his own experiments that the atom began its journey from philosophy to science. Dalton's atomic theory proposed that each chemical element is composed of atoms that are unique to that element. His theory also suggested that chemical reactions involve the rearrangement of these atoms, marking the dawn of modern chemistry. Dalton's work was pivotal as it laid the foundation for a deeper understanding of matter at its most fundamental level. His insights set the stage for future discoveries, eventually unveiling the atom's internal structure and its quantum mechanical behavior. But even Dalton's work could not predict the complexities of the atom that we would later discover. As we moved into the 20th century, advances in experimental physics led to an entirely new understanding of atomic structure. The discovery of protons, neutrons, and electrons, followed by the formulation of quantum mechanics, revolutionized our understanding. With these breakthroughs, we began to realize that the atom was not only a building block of matter, but also a key player in the intricate dance of the universe. Now we must turn our gaze outward. The atom's story is not confined to the microscopic world. It is tightly intertwined with the grand narrative of the universe itself. Enter the Big Bang Theory, a scientific explanation that seeks to unravel the mysteries of the universe's origin. The Big Bang proposes that the universe began from an incredibly hot and dense state roughly 13.8 billion years ago, and it has been expanding ever since. This theory, first introduced based on the observation that galaxies appear to be moving away from us in all directions, provided a coherent explanation for the birth of space and time. Several key pieces of evidence bolster the Big Bang Theory. The redshift of distant galaxies, which indicates that the universe is still stretching. The cosmic microwave background radiation, which is the afterglow of the Big Bang itself, now spread thinly across the cosmos, and the relative abundance of elements such as hydrogen and helium, which matches the predictions made by the theory. The Big Bang is far more than a mere origin story for the universe. It is also the foundation for understanding the formation of atoms themselves. In the earliest moments of the universe, extreme temperatures and densities allowed for the formation of the simplest atoms, primarily hydrogen and helium. This event, known as nucleosynthesis, laid the groundwork for the birth of stars and galaxies. As these simple atoms clumped together under the force of gravity, they formed stars, which in turn created heavier elements through nuclear fusion. Over billions of years, these elements scattered throughout the universe, creating the complex chemical makeup of stars, planets, and eventually, life itself. But the story doesn't end there. The Big Bang Theory not only explains the birth of the universe and the formation of atoms, but also provides a framework for understanding the universe's ongoing evolution. As galaxies move apart and space itself continues to expand, we are left with fundamental questions about the ultimate fate of the universe. Will it continue to expand indefinitely, or will it eventually collapse in a big crunch? What lies beyond the boundaries of the observable universe? These questions remind us that just as atoms remain a mysterious frontier of science, so too does the universe itself. The Big Bang Theory represents a monumental leap in human understanding, connecting the tiniest particles of matter with the vast cosmos, and reminding us of the intricate relationships that shape our existence. The exploration of atoms and the universe itself is a continuous journey, one that will forever be driven by the insatiable curiosity to understand the origins, the nature, and the fate of all things. In the moments immediately following the Big Bang, the universe was in a state so extreme and alien to our current understanding that it is nearly impossible to imagine. The temperatures and densities were staggering, far beyond anything we encounter in the cosmos today. Within the first fractions of a second, the universe was filled with a seething soup of particles, and everything was in flux. Matter and antimatter were being created and annihilated in perfect balance. This chaotic, violent period is often referred to as the Quark epoch, and it lasted only a mere microsecond after the Big Bang. During this time, the fundamental building blocks of matter, quarks and gluons, existed in a high-energy state, unbound and free from the structure we now recognize as atoms. Quarks, the elementary particles that make up protons and neutrons, roamed the universe in isolation, unable to form the stable matter we are familiar with today. It was only as the universe rapidly expanded and cooled that conditions changed, setting the stage for the formation of the first atomic nuclei. This cooling phase marked the transition into the hadron epoch, which occurred roughly 1 microsecond after the Big Bang. During this period, the universe had expanded enough for quarks to begin combining under the influence of the strong nuclear force, forming hadrons, primarily protons and neutrons. However, the temperature was still too high for these hadrons to bind into stable atomic nuclei. The universe remained an inhospitable, violent place. As time passed, the universe continued to cool and expand, and roughly 1 second after the Big Bang, it entered the lepton epoch. During this epoch, leptons, such as electrons, dominated the matter content of the universe. The universe was still filled with a dense, hot mixture of electrons, neutrinos, and photons. At this stage, the universe was a chaotic, fast-moving cloud of subatomic particles, where the interactions between these particles were constantly occurring. It wasn't until about 10 seconds after the Big Bang that neutrinos decoupled from the rest of the particles, meaning they could travel freely through space, no longer interacting significantly with the other particles. A pivotal moment in the history of the universe occurred about 3 minutes after the Big Bang. This marked the beginning of nucleosynthesis, when the temperature had cooled enough to allow atomic nuclei to form. Protons and neutrons fused to form light elements, including the majority of helium, deuterium, a form of hydrogen, and traces of lithium and beryllium. This process was crucial because it set the stage for the formation of the first elements in the universe. By about 20 minutes after the Big Bang, this phase of nucleosynthesis was largely complete. But the universe had not yet cooled enough for atoms to form. The universe continued to expand and cool, and as temperatures dropped further, the first atoms began to form. This was the beginning of the universe's transition from an incredibly hot and dense state to one more familiar to us today, one in which matter could begin to coalesce into stars, galaxies, and the other cosmic structures we see in the universe. The intense, violent early history of the cosmos was the first chapter in the long, complex story that ultimately led to the formation of everything we recognize in the universe today. At the heart of this transformation is the behavior of quarks. Quarks are among the most fundamental particles in the universe. These tiny entities combine to form hadrons, protons and neutrons, which in turn combine to form the atomic nuclei that make up all visible matter. The interactions between quarks, particularly within protons and neutrons, play a crucial role in the stability and formation of atomic nuclei, which are the foundation of all elements in the universe. During the quark epoch, quarks were not yet bound into hadrons. They existed in a free, chaotic state in what scientists call a quark-gluon plasma. In this state, the universe was so hot and dense that quarks could not form stable particles. However, as the universe expanded and cooled, it eventually reached a point where quarks began to combine due to the intense force of the strong nuclear interaction, which is mediated by gluons. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. However, for the formation of the matter we encounter every day, only the up and down quarks are essential. These 2 quarks combine in different ways to form protons and neutrons. For example, a proton consists of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. These combinations form the stable matter we recognize as atomic nuclei. Once protons and neutrons formed, they began grouping together to create atomic nuclei. The number of protons in a nucleus determines the element, e.g., hydrogen, helium, carbon, while the number of neutrons determines the isotope of that element. The interaction and arrangement of quarks within these protons and neutrons are crucial for the stability of atomic nuclei. The strong nuclear force, which is one of the 4 fundamental forces in nature, holds the quarks together within protons and neutrons. This force is extremely powerful, much stronger than the electromagnetic force that binds electrons to the nucleus, but it operates only over very short distances. understanding how quarks interact to form protons, neutrons, and atomic nuclei helps explain much of what we observe in the universe, including the variety of elements on the periodic table and the processes that power the stars. The processes of nuclear fusion and fission, key reactions in stars and nuclear reactors, are deeply rooted in the fundamental interactions of quarks within atomic nuclei. So how did the first protons and neutrons come together to form more complex elements? The answer lies in the process of nuclear fusion. Nuclear fusion occurs when atomic nuclei come close enough to each other to combine and form a heavier nucleus, releasing an immense amount of energy. This process is the source of the energy produced by stars, including our sun. In the cores of stars, high temperature and pressure create the ideal conditions for fusion to occur. For example, in the core of the sun, hydrogen nuclei, protons, fuse to form helium under temperatures reaching around 15 million degrees Celsius. The extreme temperature provides the kinetic energy necessary for protons to overcome their natural repulsion due to their positive charges. When they collide with enough force, they fuse into a heavier nucleus, releasing energy. This process not only powers the radiant heat and light of stars, but also generates elements heavier than hydrogen. These heavier elements are created in the cores of stars or during more violent events such as supernova, massive explosions that mark the end of a star's life cycle. Fusion is also responsible for the creation of most of the elements found in the universe today. Elements from helium to iron are created in stars through the process of fusion. As stars age and evolve, their cores become hotter and denser, allowing the fusion of heavier elements. But this process is limited. Once a star reaches a certain mass, it cannot fuse elements heavier than iron, leading to the death of the star and the eventual creation of new elements through supernova explosions. Thus, the creation of matter as we know it began in the primordial fireball of the early universe, with quarks and gluons gradually coalescing to form protons, neutrons, and eventually the atomic nuclei that would become the building blocks of all matter. This slow, intense process of fusion in stars continued the work started in the early moments of the universe, transforming raw, elementary particles into the rich diversity of elements that make up everything from the air we breathe to the stars in the sky. In the earliest moments of the universe, protons and neutrons, collectively known as nucleons, began to combine under the force of the strong nuclear interaction. This force, the most powerful force over short distances, acts between all nucleons and became the foundation for the creation of atomic nuclei. However, at this early stage, the universe was still far too hot for electrons to be captured into orbits around these nuclei. As a result, the particles formed what are known as bare nuclei, unaccompanied by electrons. The first significant nuclear reaction in this process occurred when a neutron and a proton merged to form the nucleus of heavy hydrogen, known as deuterium. This initial fusion was crucial, as deuterium became a stepping stone for the creation of more complex nuclei. Once deuterium was present, it could interact with additional protons and neutrons, leading to the formation of helium-3 and helium-4. Among these, helium-4 was particularly stable and became the most common product of these early fusion processes. These nuclear reactions did not happen in isolation. They released a tremendous amount of energy, which further facilitated additional fusion reactions. This chain of events led to the creation of a slight but noticeable abundance of helium-4 in the universe, alongside trace amounts of other light elements like lithium and beryllium. The specific conditions required, high temperatures and dense matter, meant that these reactions occurred predominantly during a period known as Big Bang nucleosynthesis. This phase lasted only about the first 20 minutes of the universe's existence, marking the brief window in which light elements like hydrogen, helium, and small amounts of lithium were formed. Big Bang nucleosynthesis did not stop with the creation of helium. Building on the nuclear processes that fused protons and neutrons into heavier nuclei, the formation of even lighter elements, such as lithium, occurred through a series of additional nuclear reactions. These events were part of the same nucleosynthesis period as the universe cooled sufficiently to allow stable nuclei to form, yet remained hot enough for nuclear fusion to occur. After the formation of stable helium nuclei, the next step in the cosmic chemical evolution involved the creation of lithium. Lithium, along with beryllium and boron, is classified as a light element, and its creation in the early universe was far less efficient compared to the formation of hydrogen and helium. Among the various isotopes of lithium, the creation of lithium-7, one of its more stable forms, was driven by two key nuclear processes involving helium nuclei. One of the primary pathways involved the fusion of two helium-4 nuclei, also known as alpha particles, to form beryllium-8. Beryllium-8, however, is highly unstable and typically decays back into two helium nuclei. Under the dense, hot conditions of the early universe, some beryllium-8 nuclei were able to capture another helium-4 nucleus before they decayed, which resulted in the creation of carbon-12. In another scenario, beryllium-8 could capture a neutron, transforming into beryllium-9. Beryllium-9 could then undergo further reactions, eventually leading to the formation of lithium-7. There was also another pathway for lithium formation. This route involved the direct capture of neutrons by helium-4 nuclei to form helium-5. Helium-5, however, is unstable and quickly decays into a proton and a tritium, hydrogen-3 nucleus. Tritium, in turn, could capture another neutron, turning back into helium-4, or react with deuterium, hydrogen-2, to produce helium-4 and a neutron. Over a series of such reactions, this could eventually result in the creation of lithium-7. While these processes were responsible for producing lithium and other light elements like beryllium, their efficiency was far less than that of helium production. This is mainly due to the unique conditions required for these reactions and the instability of intermediate products like beryllium-8, which often decayed before they could contribute to the creation of more complex elements. As the universe continued to expand and cool, the window for these nuclear reactions gradually closed. This marked the end of the epoch of Big Bang nucleosynthesis and froze the proportions of light elements like hydrogen, helium, and lithium into the ratios we observe today. The universe had already laid the foundational elements for the next phase in its evolution, the formation of stars, galaxies, and ultimately the heavier elements that make up the diverse cosmos we see around us. Several 100,000 years later, a monumental shift in the evolution of the universe took place, the recombination era. This period, which occurred roughly 380,000 years after the Big Bang, marks the time when the universe's temperature had dropped sufficiently, around 3000 Kelvin, allowing electrons and protons, which had previously existed in a free state due to the intense heat, to combine and form neutral hydrogen atoms. This process is known as recombination, although the term is a bit of a misnomer. This wasn't truly a recombining of previously formed atoms. Instead, it was the first time protons and electrons came together to form hydrogen. Before the recombination era, the universe was opaque to most forms of electromagnetic radiation because free electrons scattered photons, preventing light from traveling freely. This period is often referred to as the photon epoch, during which high-energy photons continuously interacted with the free electrons in a process called Thomson scattering. The universe was thus not transparent to light, and photons were constantly being absorbed and re-emitted, unable to travel far. As the universe continued to expand and cool, it eventually reached a temperature where the energy of photons was no longer sufficient to keep hydrogen ionized, i.e., where electrons and protons were separated. The density of the universe also decreased, lowering the frequency of photon-electron interactions. This reduction in interaction allowed the formation of neutral atoms, primarily hydrogen. Once neutral hydrogen atoms formed, photons were able to travel freely through space, and the universe became transparent to light. This newly transparent universe allowed photons to escape, giving rise to what we now observe as the cosmic microwave background, CMB, radiation. This radiation, a faint glow that fills the universe, is a snapshot of the universe as it was during the recombination era, offering us invaluable insights into the conditions of the early cosmos. The cooling and expansion of the universe continued, shaping the evolution of the cosmos over time. As the universe expanded from its initial incredibly hot and dense state following the Big Bang, it began to cool, similar to the way a gas cools when it expands. This expansion was not just a physical stretching of matter, but a stretching of space itself, a process known as the metric expansion of space. This expansion increased the distance between objects not bound by gravity or other forces. As space stretched, the energy density of cosmic material, including radiation and matter, diminished. The wavelength of radiation also stretched, leading to a decrease in its energy. This phenomenon is known as redshift, and it causes the cosmic microwave background radiation, once the heat radiation of a much younger universe, to be observed as microwaves today. In the very early moments of the universe's existence, the rate of expansion was not constant. A brief but extremely rapid period known as inflation occurred just after the Big Bang. During inflation, the universe expanded exponentially within fractions of a second, smoothing out any irregularities and creating a more uniform universe. After this brief period, the expansion slowed down, driven by the mutual gravitational attraction of all matter in the universe. This change in the rate of expansion would shape the universe into the form we observe today, influencing the formation of galaxies, stars, and the large-scale structure of the cosmos. About 5 billion years ago, a remarkable shift began in the universe, one that forever altered its trajectory. Observations show that the universe, after expanding steadily for billions of years, suddenly started to accelerate. This unprecedented acceleration is believed to be driven by a mysterious and as yet unexplained force: dark energy. Making up approximately 70% of the total energy content of the universe today, dark energy is thought to have a peculiar property: negative pressure. This negative pressure pushes the universe apart, overcoming the gravitational pull of matter and causing the accelerated expansion that we witness today. As the universe expanded, its temperature decreased in a direct response to this growth. Initially, the universe was hot and dense, filled with energy and particles. However, as space itself stretched, the energy cooled, leading to a gradual drop in temperature. This cooling allowed for the first simple atomic nuclei to form, marking a crucial turning point in the evolution of the cosmos. As the universe continued to cool, the formation of atoms followed. These atoms, primarily hydrogen and helium, set the stage for the creation of molecules, stars, and galaxies, which would later populate the universe with complexity and structure. But the expansion wasn't just an abstract process. It left behind a clear signature: the cosmic microwave background radiation, CMB. This faint uniform light that fills the universe today is the residual heat left from the Big Bang itself. Discovered by accident in 1964 by Arno Penzias and Robert Wilson, the CMB provides us with a snapshot of the universe when it was just 380,000 years old. At that time, the universe had cooled enough for electrons to combine with protons and form neutral hydrogen atoms, signaling the end of an era known as the recombination epoch. The discovery and study of the CMB are pivotal in supporting the Big Bang theory. It offers evidence that the universe, in its early days, existed in a hot, dense state. The near-perfect uniformity of the CMB across vast regions of space suggests that the universe had a common origin. Yet, not everything in this radiation is perfectly uniform. Tiny fluctuations, called anisotropies, are scattered throughout the CMB. These variations in temperature hold critical clues about the early conditions of the universe, revealing the tiny density differences that would eventually give rise to the formation of galaxies and other large-scale structures in the cosmos. The formation of atoms in the early universe is intrinsically linked to the CMB. As the universe cooled, it allowed free electrons and protons to combine and form neutral hydrogen atoms. This process, known as recombination, reduced the opacity of the universe, allowing photons to travel freely. Before this, photons had been constantly scattered by free electrons, making it impossible for light to travel long distances. Once atoms were formed, light could move through the universe, carrying with it essential information about the universe's early state. This moment, where light could travel freely, marked the universe's transition from a hot, opaque fog to the transparent expanse we observe today. Gravity played a subtle, yet crucial role in shaping the universe as we know it. While the universe was still young, it was mostly filled with hydrogen and helium atoms, distributed fairly evenly across space. However, these atoms weren't perfectly spread out. The CMB's temperature fluctuations revealed slight differences in density across the universe. These differences, though minuscule, were critical. Gravity, ever present, began to magnify these variations, pulling more matter into regions that were slightly denser. Over time, gravity acted as a magnifying glass, making these tiny irregularities grow into vast structures of gas, dust, stars, and galaxies. Without gravity, the primordial gas created after the Big Bang would have remained evenly distributed, and the universe would never have formed the vast, intricate structures that fill it today. As gravity gathered atoms into clouds and, eventually, stars, it provided the right conditions for nuclear fusion to occur. Inside the cores of stars, hydrogen atoms fuse to form helium, releasing immense amounts of energy in the process. This is the very reaction that powers stars like our Sun. But as stars age and exhaust their hydrogen supply, their internal pressure and temperature rise. In larger stars, this increase in temperature allows helium nuclei to fuse, forming heavier elements like carbon and oxygen through a process known as the triple alpha process. This reaction, which requires temperatures upwards of 100 million degrees Kelvin, takes place in the cores of red giant stars. For stars that are even more massive, the process of creating heavier elements doesn't stop at carbon. As the core continues to collapse, the temperature and pressure increase even further, allowing the fusion of carbon into elements like neon, magnesium, and sodium. This cycle of fusion continues, creating progressively heavier elements up to iron. Each new stage in the fusion process marks a significant step in the creation of the complex chemistry that would later become essential to life itself. Without these stellar processes, the universe would be a far simpler place, made up only of the lightest elements, hydrogen and helium. The process of stellar nucleosynthesis not only powers stars, but also fuels the creation of the elements that form planets, life, and everything we see around us. As stars die, they scatter these elements into space, enriching the interstellar medium and allowing the next generation of stars, planets, and galaxies to form. In this way, the universe's evolution is a continuous cycle of birth, death, and rebirth, all driven by the fundamental forces of nature. This intricate dance between dark energy, gravity, nuclear fusion, and the expansion of the universe has led to the creation of the vast, dynamic cosmos we observe today. From the cooling of the early universe to the formation of galaxies, stars, and the elements essential to life, each step in this process is a testament to the interplay of fundamental forces that have shaped the universe over billions of years. In the vast and ever-expanding universe, stars play a fundamental role in the creation and distribution of atoms. However, elements heavier than iron cannot be formed through the typical fusion processes occurring in the cores of normal stars. To understand why, it's essential to delve deeper into the fascinating processes that govern stellar evolution and the creation of elements. Elements heavier than iron, such as gold, uranium, and platinum, require an input of energy rather than releasing it, a crucial point in the formation of the elements that we consider valuable or essential to life. These elements are not produced through the standard fusion reactions that occur in stars during their stable lifetimes. Instead, they are forged through a much more violent and energy-intensive process. This happens either via neutron capture processes during the later stages of a star's life cycle or through the explosive events of supernova, violent and spectacular deaths of massive stars. During these catastrophic events, the intense energy and neutron flux allow for rapid neutron capture by iron nuclei, a process known as the R process, or rapid neutron capture process. This phenomenon is so powerful that it enables the synthesis of elements much heavier than iron, stretching all the way up to uranium and beyond. These newly created heavy elements are then flung into the vast expanse of space when the star explodes, enriching the surrounding cosmic environment with the building blocks of future stars, planets, and even life itself. This cosmic recycling and enrichment process is vital for the continued evolution of the universe. The materials dispersed by supernovae serve as the raw ingredients for the formation of new stellar systems, and ultimately for the development of planets and living organisms. In this way, stars act as both creators and distributors of the very atoms that compose the world around us. The process enriches the interstellar medium with elements crucial for the formation of planetary systems, providing the necessary components for life as we know it. But how exactly do stars contribute to the creation of new atoms? The answer lies in the intricate fusion processes occurring during the stable phases of a star's life, specifically in what is called the main sequence phase. This is when a star, like our Sun, burns hydrogen to form helium in its core. This hydrogen fusion releases an immense amount of energy, which not only powers the star, but also provides the light and heat we receive from it. However, the role of stars in atomic formation doesn't end with hydrogen fusion. As stars deplete their hydrogen fuel, they begin fusing helium into heavier elements. In more massive stars, this process continues, sequentially creating elements such as carbon, oxygen, and eventually iron. The higher the temperature and pressure within the star, the more complex the elements it can form, creating a rich variety of atoms that are essential for life and for the very structure of the universe. The sequence of fusion reactions that defines a star's life cycle is not limitless, however. Once a star has produced iron in its core, further fusion becomes energetically unfavorable. This is because iron has the highest binding energy per nucleon, making it the most stable of all elements. At this point, the star can no longer generate enough energy to counterbalance the force of its own gravitational collapse. The star begins to implode, leading to a dramatic explosion known as a supernova. Supernovae are not merely spectacular displays of energy. They are crucial for the creation of the universe's heavier elements. The extreme conditions inside a supernova, enormous heat, immense pressure, and an overwhelming flood of neutrons, allow for the rapid capture of neutrons by atomic nuclei, triggering the formation of elements heavier than iron. Among the precious elements created in this process are gold, platinum, and uranium, metals that have immense value on Earth. These heavy elements, formed in the fiery heart of a dying star, are then blasted into space during the supernova explosion, enriching the surrounding interstellar medium with atoms that will eventually become part of new stars, planets, and even life itself. Through this cosmic cycle, stars function not only as the birthplace of new atoms, but also as the distributors of these atoms across the galaxy. When the material ejected from dying stars settles into the interstellar medium, it mixes with the remaining gases, forming the raw materials for future generations of stars, planets, and other celestial bodies. In the quest to understand how atoms form in space, telescopes serve as invaluable tools, providing crucial insights into the processes that take place within stars and galaxies. By observing the light emitted from distant stars, galaxies, and other celestial objects, astronomers can discern the elements present in these far-off bodies and the nuclear processes that give rise to them. At the heart of these observations lies the science of spectroscopy. Spectroscopy allows scientists to break down the light from celestial bodies into its component colors, much like a prism separates light into a rainbow. This light spectrum contains distinct absorption and emission lines, which act as a unique fingerprint for each element or molecule. By analyzing these lines, astronomers can identify the elements that make up distant stars, galaxies, and other celestial bodies. For example, by studying the spectra of stars, scientists can determine the abundance of hydrogen, helium, and heavier elements such as carbon and oxygen. These observations provide valuable insights into the star's life history, revealing details about how it has formed, evolved, and eventually died. The presence of certain isotopes within stellar spectra can even give scientists clues about the nuclear reactions occurring deep within a star's core, such as those responsible for the synthesis of heavier elements. Nucleosynthesis, the process of creating heavier elements from lighter ones within stars, is one of the most critical stages in stellar evolution. It's not only essential for the life cycle of individual stars, but also for the broader evolution of galaxies. As stars die and expel their enriched material into space, they provide the building blocks for the formation of future stars and planetary systems. This process of atomic creation and distribution is one of the driving forces behind the chemical evolution of the universe. Telescopes equipped with advanced spectroscopic instruments extend our ability to observe atomic formation beyond our own Milky Way galaxy, reaching out to distant galaxies and even the earliest stars formed after the Big Bang. These observations provide a broader understanding of the chemical evolution of the universe. By comparing the light emitted by distant galaxies with that from galaxies closer to home, Astronomers can trace how atomic formation and element enrichment have progressed over the course of billions of years. The development of more sophisticated telescopes and spectroscopic techniques has led to some of the most profound discoveries about the atoms in space. These findings not only deepen our understanding of the cosmos, but also emphasize the central role that atoms play in the formation and evolution of the universe. From the creation of stars to the formation of planets, and ultimately, the rise of life, atoms are the fundamental building blocks that shape everything we know. Through the lens of modern telescopes, we gain a clearer picture of the universe's chemical makeup and the intricate processes that continue to shape it. In this grand cosmic tale, stars are more than just shining lights in the sky. They are the architects of the universe's atomic structure, the forges in which elements are born, and the messengers that carry those elements across the vast reaches of space. Through the powerful processes of nuclear fusion and stellar death, they give birth to the very atoms that compose the world around us, atoms that will go on to form new stars, new planets, and perhaps in the distant future, new forms of life. In the aftermath of the Big Bang, just minutes after the universe began its tumultuous expansion, two elements, hydrogen and helium, emerged as the building blocks of all matter. These two elements dominate the cosmos, making up the majority of ordinary matter we observe today. Hydrogen, the simplest and most abundant element, along with helium, were formed in an intense period of nuclear reactions known as Big Bang nucleosynthesis. The discovery of these elements' prevalence throughout the universe is a crucial pillar of evidence supporting the Big Bang theory. Cosmic observations, from the faint glow of the cosmic microwave background radiation to the detailed studies of distant galaxies and quasars, have reaffirmed that hydrogen and helium are not only common in the universe, but are essential in shaping its structure. These findings illustrate a fundamental aspect of the universe's composition, helping scientists trace the origins of matter and the conditions that led to the formation of galaxies, stars, and eventually planets. The significant amounts of hydrogen and helium in galaxies also suggest that the early universe was, for a time, dominated by these two elements, with everything else, metals, compounds, and complex structures, coming much later as stars evolved. Stars, the cosmic furnaces where matter undergoes nuclear fusion, are also the factories for creating heavier elements. Through detailed stellar spectroscopy, astronomers have identified a variety of elements beyond hydrogen and helium, such as carbon, nitrogen, oxygen, and iron, in the atmospheres of stars. These observations corroborate the theory of stellar nucleosynthesis, which explains how stars create elements through fusion at their cores. As stars evolve, they undergo fusion reactions, fusing lighter elements like hydrogen into heavier ones, ultimately creating the elements that make up planets, life, and even ourselves. It is in the hearts of stars during their violent deaths, whether in supernovae explosions or during the final stages of a star's life, that elements heavier than iron are forged. These heavy elements, including gold, uranium, and platinum, are scattered into the cosmos, enriching the interstellar medium and ensuring the continued cycle of star birth and death, a process crucial for the formation of planetary systems and the development of life as we know it. The vast emptiness between stars, known as the interstellar medium, is far from barren. Through the power of spectroscopy, scientists have discovered that even in these seemingly desolate regions, complex molecules thrive. Water, ammonia, and organic molecules like methanol have been detected in the cold, dense clouds of space. These molecular compounds are not just intriguing, they are fundamental to understanding how chemical complexity evolves in the universe. The presence of such molecules hints at the pathways by which the building blocks of life could form in space. As gas clouds collapse and form stars, these molecules may be swept into the atmospheres of newly forming planets or even incorporated into comets and asteroids, potentially serving as the seeds for life's chemical building blocks. The study of molecules in space thus plays a vital role in our search for the origins of life and understanding the conditions that could foster the development of living organisms on other worlds. Telescopes not only reveal the structure and composition of far-off stars, but also allow us to study the isotopic composition of elements found in space. These isotopic variations, differences in the number of neutrons in atomic nuclei, can provide invaluable insights into the processes that shape the early solar system. Comparing the isotopes found in distant cosmic objects to those on Earth can help scientists unravel the mysteries of how our solar system came into being, what it was like in its formative years, and how the elements we depend on were distributed across the galaxy. The study of isotopic anomalies also opens a window into the history of supernova, stellar explosions that seeded the universe with heavy elements. These isotopes are like ancient relics that reveal the story of how matter was processed and recycled through the cosmos. Helium-3 and deuterium, two rare isotopes, have become essential tools for understanding the universe's early moments. These isotopes, found in the atmospheres of gas giants like Jupiter and Saturn, as well as in the interstellar medium, are remnants of the primordial soup that existed just minutes after the Big Bang. Their relative abundances offer a unique fingerprint of the conditions during the earliest phases of the universe. By studying these isotopes, astronomers can refine their models of cosmic evolution and gain a deeper understanding of the forces at play in the universe's infancy. These isotopic traces allow scientists to test predictions about the universe's first moments, offering a glimpse into the processes that shape the cosmos. Understanding their distribution helps us confirm theories about the early universe, providing insights into the birth of elements and the formation of the first atoms in the aftermath of the Big Bang. Particle accelerators, like the Large Hadron Collider, LHC, at CERN, and the Relativistic Heavy Ion Collider, RHIC, in the United States, are among the most powerful tools physicists have to explore the fundamental particles and forces that govern the universe. By accelerating particles to speeds close to the speed of light and then colliding them, these machines recreate the extreme conditions that existed moments after the Big Bang. These high-energy collisions generate temperatures millions of times hotter than the core of the Sun, briefly replicating the dense hot state of the early universe. In these collisions, the particles break down into their most basic components, revealing a state of matter known as quark-gluon plasma. This exotic substance, believed to have existed during the first moments of the universe, allows scientists to study the behavior of quarks and gluons, the fundamental building blocks of matter. By recreating this primordial state of matter, physicists gain a deeper understanding of the strong force, the force that binds quarks together to form protons and neutrons, and by extension, the matter that makes up everything we observe in the universe. These experiments at particle accelerators have far-reaching implications, not only for understanding the early universe, but also for investigating some of the deepest questions in physics. From the origins of matter and antimatter to the mysterious nature of dark matter, these experiments push the boundaries of our knowledge, offering new insights into the forces that shape the cosmos. Theoretical physicists play a crucial role in unlocking the mysteries of the universe by developing models and frameworks that explain the behavior of atoms and their components. Central to their work are theories like quantum mechanics and quantum field theory, which provide the mathematical tools to understand the interactions of particles at atomic and subatomic scales. These theories have revolutionized our understanding of the atomic world, revealing not only the structure of atoms, but also the nature of the forces that govern their behavior. For instance, quantum mechanics describes how particles like electrons move and interact in probabilistic terms, rather than following fixed paths. This shift in perspective has profound implications, explaining phenomena like chemical bonding, atomic spectra, and the properties of materials. The work of theoretical physicists doesn't stop at explaining known phenomena, they also predict new ones. The prediction of antimatter, for example, was once purely theoretical before it was confirmed experimentally. Moreover, theoretical physics extends its reach to the cosmos, offering insights into the birth of the universe. Theories of cosmic inflation, developed by physicists like Alan Guth, describe how the universe expanded exponentially in its earliest moments, setting the stage for the formation of matter and the development of the cosmos we know today. In collaboration with experimental physicists, theoretical physicists continue to refine models based on real-world data, testing predictions, and ensuring that their theories align with observable phenomena. Together, they drive our understanding forward, uncovering the deepest truths about the universe and its origins. The concept of the atom has undergone a profound transformation over the past century, evolving from a simplistic view to a complex quantum mechanical model that underpins much of modern physics and chemistry. Early in the 20th century, J.J. Thomson's plum pudding model of the atom, where electrons were embedded within a positively charged sphere, was the accepted view. However, this was soon overturned by Ernest Rutherford's famous gold foil experiment, which revealed that atoms have a tiny, dense nucleus surrounded by electrons, a groundbreaking discovery that reshaped our understanding of atomic structure. Niels Bohr's model of the atom, introduced in 1913, further refined this understanding by incorporating quantum theory. Bohr proposed that electrons occupy fixed orbits around the nucleus and can only occupy specific energy levels, a revolutionary idea that explained the spectral lines of hydrogen with great accuracy. However, it wasn't until the development of quantum mechanics in the 1920s, with the work of Schrödinger, Heisenberg, and others, that a more complete framework emerged. The Schrödinger equation in particular introduced the concept of electron probability clouds, replacing the idea of fixed orbits with a probabilistic model of electron positions. The journey from classical models to quantum mechanics didn't stop with electrons. We now know that protons and neutrons, once thought to be indivisible particles, are themselves made of quarks bound by gluons. This realization has deepened our understanding of the strong nuclear force, one of the fundamental forces of nature, and has led to the development of the standard model of particle physics, a framework that describes the interactions of all known elementary particles. This ongoing evolution of atomic theory continues to shape the future of science, providing us with a richer, more nuanced understanding of the universe at the most fundamental level. Whether investigating tiniest particles in particle accelerators or delving into the nature of dark matter and the forces that govern atomic interactions, the study of atoms and their constituent parts remains at the forefront of scientific exploration. At its core, quantum mechanics offers a radically different view of reality compared to classical physics. Where classical physics was deterministic, predicting exact outcomes based on inputs, quantum mechanics introduces uncertainty and probability into the equation. This framework describes the behavior of atoms and subatomic particles, where particles do not follow fixed paths but instead exist in a superposition of possibilities until measured. The principles of quantum mechanics are essential for understanding phenomena at the smallest scales, from the behavior of electrons in atoms to the strange interactions between particles in high-energy experiments. Quantum mechanics has become the foundation of modern physics, underpinning technologies from semiconductors to quantum computers, and continues to shape our understanding of the universe in profound ways. Through the lens of quantum theory, we are unlocking new realms of possibility, whether in understanding the fabric of space-time itself or seeking to uncover the mysteries of dark energy and dark matter. Quantum mechanics is one of the most groundbreaking fields of science, shaping our understanding of the universe at its most fundamental level. One of its core principles is wave-particle duality, a concept that defies the classical logic we once relied upon to understand the world. In essence, this principle suggests that every particle, whether it's a photon, electron, or any other quantum entity, can exhibit both particle-like and wave-like properties depending on the situation. This revolutionary idea has profound implications for how we perceive the behavior of particles at the microscopic scale. A particularly compelling application of wave-particle duality is in the behavior of electrons within atoms. Before the advent of quantum theory, scientists believed that electrons orbited the nucleus much like planets orbit the sun. This model, known as the Bohr model, suggested that electrons moved in neat, circular paths around the nucleus. However, the quantum mechanical view challenges this picture entirely. Electrons are not confined to fixed orbits. Instead, they are described by wave functions, which predict a range of probable locations where the electron might be found at any given time. These regions are not simply random, rather they form distinct patterns known as electron orbitals, each with a specific shape and energy level. The tool that allows us to calculate these wave functions is the Schrödinger equation, one of the cornerstone equations of quantum mechanics. This equation provides a mathematical framework that tells us the likelihood of finding an electron in a particular location. But the Schrödinger equation doesn't give us an exact position. Instead, it gives us a cloud of probabilities, a region where the electron is most likely to be found. This probabilistic nature of quantum mechanics helps explain why atomic behaviors, such as the arrangement of electrons in atoms, chemical bonding, and the way atoms absorb or emit light, occur in specific quantized patterns. These behaviors are discrete, meaning they happen in distinct steps or levels rather than continuously. In addition to wave-particle duality, quantum mechanics introduces the concept of quantum superposition, which states that particles can exist in all possible states simultaneously until an observation is made. This principle is most famously illustrated by Schrödinger's cat thought experiment. Imagine a cat in a sealed box with a device that has a 50% chance of killing the cat based on the decay of a radioactive atom. According to quantum mechanics, the cat is both alive and dead until someone opens the box to observe it. It's only at that moment that the wave function collapses, and the cat is found to be either alive or dead, but not both. Another key feature of quantum mechanics is the Heisenberg uncertainty principle. This principle asserts that there are fundamental limits to how much we can know about a particle's properties. Specifically, it states that we cannot simultaneously know both the exact position and the exact momentum of a particle. The more precisely we measure one property, the less precisely we can measure the other. This is not due to a limitation in our measurement tools, but rather a fundamental feature of nature itself. This uncertainty becomes particularly significant at the atomic and subatomic levels, where the behavior of particles cannot be predicted with absolute certainty. It is this principle that has profound implications for the way atoms and molecules interact and how we understand the fundamental limits of our knowledge. Quantum mechanics also offers insight into phenomena that classical physics cannot explain. One such phenomenon is quantum fluctuations. According to the Heisenberg uncertainty principle, there are temporary, spontaneous changes in the amount of energy at a point in space. These fluctuations can lead to the creation of particle-antiparticle pairs, which materialize out of the vacuum and almost instantaneously annihilate each other, returning the borrowed energy to the vacuum. Though these particles appear and disappear in the blink of an eye, their effects can be measured in certain circumstances, such as the Casimir effect and the Lamb shift. The Casimir effect, for instance, manifests as a small force that pushes two uncharged parallel plates together when they are placed in a vacuum. This force arises from the fact that quantum fluctuations between the plates are suppressed compared to the space outside, creating a difference in pressure that causes the plates to move. The Lamb shift, another measurable phenomenon, is a slight change in the energy levels of an atom, a result of the interaction between the atom and the fluctuating vacuum energy. In cosmology, quantum fluctuations play a crucial role in the formation of the universe itself. During the inflationary period, which occurred fractions of a second after the Big Bang, minuscule fluctuations in the density of the universe were amplified, leading to the large-scale structures that make up the cosmos today: galaxies, galaxy clusters, and the vast voids between them. These fluctuations were the seeds of all that we observe in the universe, from stars to supermassive black holes. Despite the success of quantum mechanics in explaining atomic and subatomic phenomena, many unanswered questions remain that challenge our current understanding of the universe. One of the most perplexing is the issue of wave function collapse. As mentioned earlier, quantum mechanics describes particles in terms of probabilities until they are observed. At that point, the wave function collapses and the particle assumes a definite state. But what exactly causes this collapse, and why does it happen only upon observation? This remains one of the deepest mysteries in the interpretation of quantum mechanics, forcing physicists to question the very nature of reality and the role of the observer. Another area that remains unresolved is quantum gravity. While general relativity successfully explains the behavior of massive objects like stars and black holes, and quantum mechanics rules the subatomic world, the two theories currently be reconciled. This incompatibility becomes particularly problematic when considering the early universe, where both gravitational forces and quantum effects would have been intertwined. Understanding how these two frameworks can be unified remains a major pursuit in theoretical physics. Finally, the elusive nature of dark matter continues to confound scientists. While we know dark matter exists because of its gravitational effects on galaxies and larger cosmic structures, we still have little understanding of what it is made of. Dark matter does not emit light or interact with ordinary matter in any of the ways we are familiar with, making it difficult to detect. But its presence is undeniable, and unraveling its mysteries is critical for understanding the evolution of the universe. In conclusion, quantum mechanics has revolutionized our understanding of the universe, from the smallest particles to the grandest cosmological structures. It has provided us with powerful tools to describe the behavior of atoms and molecules, explaining phenomena that classical physics could not. Yet, as we peer deeper into the quantum world, we are faced with questions that challenge the very fabric of our understanding. As physicists continue to explore these mysteries, the potential for discovery is as vast and infinite as the universe itself. At the quantum level, the role of dark matter remains one of the universe's greatest mysteries. Despite its overwhelming presence, making up approximately 85% of the universe's total matter, its interaction with ordinary matter is poorly understood. This enigmatic substance, which doesn't emit, absorb, or reflect light, offers intriguing possibilities that could unlock new dimensions in our understanding of atomic formation, particularly during the earliest moments of the universe's existence. If we are able to uncover the secrets of dark matter, it could illuminate how atomic structures first emerged in the wake of the Big Bang, offering a glimpse into the primordial forces shaping the cosmos. Another profound conundrum in modern physics is the matter-antimatter asymmetry. Quantum mechanics cannot fully explain why, following the Big Bang, the universe contains far more matter than antimatter. According to theory, equal amounts of both should have been produced, but an imbalance remains, leaving us with the matter-rich universe we observe today. This mysterious imbalance not only challenges our understanding of the early universe's composition, but also tests the fundamental laws of physics that govern atomic and particle formation. Without solving this riddle, our grasp on the very fabric of the cosmos will remain incomplete. The perplexing phenomenon of quantum entanglement introduces further layers of complexity. In entanglement, particles become intertwined in such a way that the state of one instantaneously influences the state of another, regardless of the distance between them. This spooky action at a distance, as Einstein once called it, raises important questions about the nature of information transfer and causality. Could this quantum behavior have played a crucial role in the early interactions that governed the formation of atomic structures in the fledgling universe? As we venture deeper into these mysteries, our understanding of atomic processes may evolve in ways we cannot yet predict. The creation of atoms. Science meets mythology. The scientific explanation for the formation of atoms can be traced through the principles of nuclear physics and cosmology, but this understanding exists in parallel with a rich tapestry of cultural interpretations and creation myths that attempt to explain the origin of matter. From the ancient philosophers of the West to the spiritual teachings of the East, different cultures have developed unique narratives about the birth of the universe and the fundamental building blocks of reality. Hashem, Western philosophical traditions, the origins of the concept of indivisible matter can be traced back to ancient Greece, particularly through the work of philosophers such as Democritus and Leucippus. These thinkers introduced the idea of the atomos, meaning uncuttable, a tiny, indivisible particle that forms the basis of all matter. This concept, while initially a speculative philosophical idea, had laid the groundwork for what would later evolve into modern atomic theory. For the ancient Greeks, everything in the universe, both tangible and intangible, was believed to be composed of these atoms, set in motion by the void between them. Hindu cosmology, Hinduism, with its intricate cosmological framework, offers a cyclical view of creation, destruction, and rebirth. In ancient Hindu texts like the Vedas and Upanishads, the universe is thought to be made of 5 fundamental elements: earth, water, fire, air, and ether, collectively known as the Panchabhuta. While these elements do not directly correspond to the modern concept of atoms, they serve as philosophical counterparts, representing the building blocks of the universe. In this vision, the interplay of these elements drives the cycles of creation, maintenance, and dissolution, revealing an intimate connection between matter and the cosmos. Buddhist philosophy and Buddhism, particularly within the Abhidharma teachings, there is the notion of dharmas, minute, impermanent phenomena that together constitute the fabric of reality. These dharmas are not atoms in the conventional sense, but can be seen as the most fundamental units of existence. The Buddhist view emphasizes the impermanence and interdependence of all things, like reflecting the belief that the universe is in a constant state of flux. Rather than positing a permanent, indivisible particle as the foundation of reality, Buddhist philosophy suggests that the universe is composed of ever-changing, interconnected processes, with no singular, unchanging essence at its core. Indigenous perspectives. Many indigenous cultures have their own unique stories about the creation of the universe, often centered around a harmonious balance between natural forces. For example, Native American tribes and Aboriginal Australians share creation myths that describe the formation of the world in terms of elemental forces, spirits, and the sacred relationships between humans and the. While these stories may not explicitly reference atoms, they convey a profound understanding of the interconnectedness of all things. These narratives often emphasize balance, unity, and the life-giving forces that shape the universe, offering a perspective that sees matter not as a static structure, but as a dynamic interplay of energies and forces. Islamic and Middle Eastern views. During the Islamic Golden Age, scholars like Alhazen and Avicenna explored the nature of matter in ways that integrated both philosophical and theological principles. Drawing from Greek atomism, they considered the fundamental building blocks of the universe but viewed them as part of a divine order. In this view, continuous creation and organization of atoms was seen not as a random process, but as manifestation of God's will. The exploration of the material world was, for many of these thinkers, an exploration of the divine, with the structure of the universe reflecting a higher cosmic order. Science, ethics, and the pursuit of knowledge. As humanity continues to probe the origins of the universe and the fundamental nature of matter, the journey is not without its ethical considerations. Research into the cosmos, particularly in fields like cosmology, astrophysics, and particle physics, often requires massive investments in resources and infrastructure. Projects such as the Large Hadron Collider, LHC, at CERN demand not only financial resources, but also significant energy consumption. Critics argue that these resources might be better directed toward addressing more immediate human needs, such as poverty alleviation, healthcare, and education. However, proponents of these projects argue that the pursuit of knowledge, particularly in understanding the origins of the universe, has the potential to yield breakthroughs with far-reaching applications. Advancements in technology, medicine, and even our understanding of the laws of nature itself can often emerge from fundamental research. By unraveling the mysteries of dark matter, quantum entanglement, and atomic formation, we may unlock new technologies and insights that will benefit humanity in ways we cannot yet foresee. The ethical debate continues, but the quest for knowledge, however resource-intensive, remains one of humanity's most ambitious and transformative endeavors. The environmental implications of operating large-scale scientific equipment, particularly those involved in high-energy research, raise complex and pressing ethical concerns. These concerns are not only related to the energy demands, but also to the environmental impact of constructing and maintaining such advanced facilities. For example, particle accelerators, which require immense amounts of energy to simulate the fundamental forces of nature, have a substantial carbon footprint. This places significant pressure on the global scientific community to develop methods that minimize their environmental impact. Given the growing urgency of combating climate change, there is a need for more sustainable practices in energy consumption. Renewable energy sources, such as solar and wind power, could play a crucial role in mitigating the carbon emissions associated with these scientific endeavors, offering a pathway to reconcile the pursuit of knowledge with environmental responsibility. In addition to these practical considerations, the exploration of the cosmos and the origins of the universe introduces profound philosophical and existential questions. Such inquiries have the potential to reshape humanity's understanding of its place in the universe. The ethical implications of uncovering the mysteries of our existence, for instance, could pose significant challenges. These discoveries may bring us closer to understanding not only how the universe began, but also what risks humanity might face in the future, especially with the rise of emerging technologies. As we gain deeper insights into the nature of reality, we must confront difficult questions about the moral responsibilities that accompany such knowledge. Can we control the technologies we develop? And how do we ensure that the pursuit of such transformative discoveries does not lead to unintended consequences? Furthermore, these cosmic revelations can clash with cultural, religious, and philosophical worldviews. Many of the foundational beliefs about creation, existence, and the nature of life are deeply rooted in specific traditions and cultural narratives. As scientific understanding continues to challenge these perspectives, the ethical dilemma becomes one of how to balance the dissemination of scientific knowledge with respect for diverse viewpoints. Educational institutions, media outlets, and public forums must navigate this delicate terrain, encouraging scientific literacy while remaining sensitive to the beliefs of individuals and communities. This is not merely a matter of academic freedom, but one of social responsibility, where the promotion of knowledge should always be paired with thoughtful engagement and respect for the complexities of human belief systems. Equally important is the responsibility to consider the long-term impact of today's scientific discoveries on future generations. The technological advancements and knowledge we accumulate now will likely shape the world for centuries to come, influencing not only human civilization but also the broader ecosystem. It is crucial to recognize that the choices made in the present will have lasting repercussions, especially as new technologies, ranging from artificial intelligence to biotechnology, emerge at an accelerating pace. Our innovations today will set the stage for the challenges and opportunities that future generations will face. As stewards of this knowledge, we must consider the broader implications of our work and ensure that the legacies we leave behind are positive ones for both humanity and the planet. As the fields of quantum mechanics and cosmology continue to evolve, it is likely that our understanding of atomic origins will undergo significant transformations. New theories and discoveries may radically challenge or expand upon the models we currently use to explain the universe's early stages. For example, the development of unified field theories could lead to a deeper understanding of how the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, interact, especially during the birth of the universe. Such a theory could potentially explain how these forces combined to produce the first particles, setting the stage for the formation of atoms and, by extension, everything we know today. The concept of quantum gravity is another area of growing importance. It seeks to explain the nature of gravity at the quantum scale, an area where classical physics breaks down. By exploring quantum gravity, researchers could gain insights into how particles behave during the Planck epoch, the earliest moments of the universe, when conditions were incredibly extreme. This could reshape our understanding of space-time itself and provide a more unified framework for understanding particle formation. Additionally, the multiverse theory, suggesting that there may be multiple, potentially infinite universes, opens up fascinating possibilities. If proven true, it could lead to an entirely new way of understanding atomic structures and the laws that govern them, perhaps revealing forms of matter that are completely unfamiliar to us. The discovery of dark matter, a mysterious substance that is believed to make up about 27% of the universe's mass, could further illuminate the conditions under which atoms formed in the early universe. Although dark matter does not interact with light, its gravitational effects on visible matter are measurable, and it could hold key clues about the nature of the early universe. Understanding dark matter's role could help explain the mass and energy distribution that influence the formation of the first atoms and particles, potentially offering new directions for theoretical research in particle physics. Moreover, advancements in particle accelerator technology and observational astronomy are pushing the boundaries of what we can study about the cosmos. These tools enable scientists to simulate conditions closer to the Big Bang, offering an unprecedented opportunity to test current theories and models. By replicating early universe conditions with increasing accuracy, we might uncover new, surprising insights about the first moments of atomic creation, possibly requiring entirely new theoretical frameworks to account for these findings. Such discoveries could significantly alter the trajectory of scientific understanding in fields ranging from cosmology to quantum physics. Dark energy, which is thought to be responsible for the accelerated expansion of the universe, remains one of the most perplexing phenomena in modern physics. Unlike dark matter, which interacts with gravity and affects the motion of galaxies, dark energy exerts a repulsive force on the cosmic scale, driving the universe apart. First identified through observations of distant supernovae in the late 1990s, dark energy makes up about 68% of the total energy content in the universe. However, its exact nature is still largely unknown. While dark matter interacts with atomic matter through gravity, dark energy's effect is primarily on the large-scale structure of the universe. At the atomic level, its influence is minimal, but on the cosmic scale, it is a dominant force. As scientists continue to probe the mysteries of dark energy, they may uncover new theories that connect it to the formation of matter or to other fundamental forces. Understanding dark energy's role could be key to unlocking many of the unanswered questions about the universe's past, present, and future. The pursuit of these discoveries requires a careful balance of intellectual curiosity, technological innovation, and ethical consideration, as the implications of what we learn could reshape our understanding of the cosmos and our place within it. However, dark energy plays a pivotal role in shaping the vast and intricate structure of the universe, indirectly influencing the creation and distribution of galaxies, galaxy clusters, and ultimately the formation of atomic matter. This elusive and invisible force affects the cosmos at the largest scales, helping to determine how galaxies are structured and how stars and planetary systems arise within them. Despite its profound impact, the precise nature of dark energy remains one of the most captivating enigmas in modern physics. Often conceptualized as a cosmological constant, dark energy was first introduced by Albert Einstein in his field equations of general relativity, a term he initially used to balance the equations and account for a static universe. Later, Einstein famously referred to it as his biggest blunder, after the discovery that the universe is actually expanding. However, some contemporary theories propose that dark energy is not simply a static constant, but rather a dynamic field, akin to the electromagnetic field, possessing its own distinct particles and energy dynamics. This alternative perspective suggests that dark energy could fluctuate over time or even manifest in unexpected forms. As technology advances, new discoveries are anticipated, especially through the use of advanced space telescopes and observatories, which may finally illuminate the true nature of dark energy. Despite its overwhelming influence on cosmic scales, dark energy remains elusive, unable to be directly detected even in the atomic realm. In contrast, dark matter is another mysterious cosmic entity that, like dark energy, eludes direct detection. Dark matter does not emit, absorb, or reflect light, rendering it invisible to conventional telescopes. Yet, its existence is inferred through its gravitational effects on visible matter, such as stars and galaxies. Dark matter accounts for about 27% of the universe's total mass energy content, far surpassing the amount of ordinary matter, which makes up stars, planets, and all known life. Although dark matter is an essential element in our understanding of the universe, its exact nature remains one of the most profound questions in physics. Its properties are only speculated upon, based on the gravitational influence it exerts on visible matter and the large-scale structures of the universe. Dark matter primarily impacts the formation of atomic matter not by direct interaction, but through its gravitational effects. After the Big Bang, the universe was in a state of near-perfect uniformity, a vast expanse of energy and matter with only the faintest fluctuations in density. These minuscule variations in density, known as quantum fluctuations, acted as the seeds for the universe's later structure. Dark matter, with its gravitational pull, began to clump around these fluctuations, gradually building gravitational wells that attracted ordinary matter. This process amplified the gravitational fields in certain regions, creating conditions ripe for the formation of stars and galaxies. Without dark matter's gravitational influence, the strength of these fields would have been insufficient to pull together the necessary mass to form galaxies, potentially leading to a universe that looked vastly different from the one we observe today. The presence of dark matter was instrumental in guiding the formation of dense regions within the universe where stars could form and galaxies could take shape. These regions, influenced by the gravitational pull of dark matter, eventually coalesced into the stars and planetary systems that populate our universe. While dark matter does not interact with ordinary atomic matter via electromagnetic forces, meaning it does not directly affect processes like nuclear fusion, its influence on galaxy formation was crucial in setting the stage for those processes to occur. In effect, dark matter provided the necessary gravitational scaffolding for the creation of environments where nuclear reactions could occur, enabling the formation of heavier elements within stars. These elements, in turn, are essential for the chemical diversity we observe throughout the universe today. In the early universe, shortly after the Big Bang, antimatter played a pivotal role in shaping the fundamental structure and composition of the cosmos. Antimatter is similar to ordinary matter in terms of mass and volume, but its electrical charges are reversed. For example, an electron, which is a fundamental particle of matter, carries a negative charge, while its antimatter counterpart, the positron, carries a positive charge. This fundamental difference in charge is what distinguishes antimatter from matter and leads to its unique properties. In the chaotic, high-energy environment immediately following the Big Bang, both matter and antimatter were created in large quantities. The universe was an incredibly hot and dense place, filled with energetic photons that could interact with one another and convert their energy into particle-antiparticle pairs. This process, predicted by quantum field theory, led to the creation of many fundamental particle pairs, electrons and positrons, protons and antiprotons, neutrons and antineutrons, throughout the early universe. Theoretical predictions, along with observations of cosmic background radiation and other astronomical data, suggest that matter and antimatter were produced in nearly equal amounts. However, despite these predictions, a slight imbalance between matter and antimatter occurred, leading to the dominance of matter in the present-day universe. This asymmetry, often referred to as the matter-antimatter imbalance, is one of the key puzzles in cosmology, as it remains unclear why the universe today consists primarily of matter, with only trace amounts of antimatter. This mystery continues to be a subject of intense study and may provide critical insights into the fundamental laws of physics. In essence, both dark energy and dark matter, along with antimatter, are central players in the grand narrative of the universe's formation. Dark energy shapes the large-scale expansion of the cosmos. Dark matter provides the gravitational structure necessary for galaxies and stars to form, and antimatter played a crucial role in the early moments of the universe, determining the composition of matter. Together, these mysterious and unseen forces are fundamental to the universe's structure, yet their true nature remains hidden, driving scientists to seek answers that may radically alter our understanding of the cosmos. As new technologies and deeper insights emerge, the mysteries of these components may one day reveal the intricate processes that have shaped the universe from its inception to the present day. However, a subtle asymmetry in the laws of physics favored the creation of matter over antimatter, though only by an incredibly small margin. For every billion pairs of particles and antiparticles that were created in the early moments of the universe, there was a single extra particle of matter. This minuscule surplus is profoundly significant. As the universe cooled, particles began to combine and form atoms, while matter and antimatter met and annihilated one another upon contact, releasing vast amounts of energy in the form of photons. If matter and antimatter had been perfectly balanced, This annihilation would have left behind nothing but pure energy, leaving the universe devoid of the essential building blocks required to form stars, planets, and galaxies. This slight imbalance in favor of matter over antimatter is a fundamental mystery, and it stands as one of the most significant unsolved questions in modern physics. Despite years of research, scientists have not yet arrived at a complete understanding of why this asymmetry exists. Theories have emerged, with one of the most prominent being CP violation. This theory proposes that the laws governing matter and antimatter are not identical, causing subtle differences in their behavior. CP violation has been observed in specific subatomic particles under controlled conditions in laboratories on Earth, providing some tantalizing clues. However, it has yet to provide a comprehensive explanation of the matter-antimatter imbalance that occurred in the early universe. The concept of extra dimensions is another fascinating avenue of exploration in theoretical physics, often linked to the complex realm of string theory. According to string theory, the fundamental particles that make up matter are not point-like objects, but are instead tiny, vibrating one-dimensional strings. These strings vibrate at specific frequencies, and the characteristics of particles we observe in the universe, such as their mass and charge, are determined by how these strings vibrate. String theory suggests that these strings may exist in more than the familiar 4 dimensions of spacetime that we experience in our everyday lives. In fact, string theory posits that there could be many additional dimensions, possibly up to 10 or 11, all of which are compactified or curled up at scales so minuscule that they are effectively undetectable by current experimental tools. If these additional dimensions truly exist, they may play a crucial role in shaping the very structure of the universe. Some theorists suggest that they could offer an explanation for some phenomena that the standard model of particle physics cannot fully explain. For instance, the standard model leaves questions unanswered about why certain particles have the masses they do, or why the fundamental forces of nature, such as gravity, electromagnetism, and the strong and weak nuclear forces, are scaled the way they are. If string theory or related multidimensional frameworks are correct, interactions within these extra dimensions could subtly influence atomic and subatomic particles, possibly accounting for some of the mysteries that still puzzle physicists. However, as of now, no direct experimental evidence has been found to confirm the existence of these extra dimensions. While high-energy experiments like those conducted at the Large Hadron Collider, LHC, aim to probe the deepest secrets of particle physics, they have yet to provide concrete evidence of extra dimensions. Researchers at the LHC are looking for indirect signs of these hidden dimensions, such as unexplained patterns of energy and momentum that might suggest that particles are leaking into these higher dimensional spaces during collisions. While these experiments are pushing the frontiers of knowledge, the existence of extra dimensions remains unproven, and our understanding of the universe's structure continues to evolve. Among the most mysterious and exciting areas of research in particle physics are the exotic particles that defy classification within the standard model. These particles often exhibit strange or unexpected properties that challenge our current understanding of physics and may indicate the presence of new, undiscovered physical phenomena. Exotic particles may hold the key to unlocking a more complete theory of the universe, one that transcends the limitations of the current models. The study of these elusive particles could potentially open up entirely new realms of physics, offering insights that could revolutionize our understanding of the universe at the most fundamental level. In the vast and mysterious world of particle physics, few concepts capture the imagination as profoundly as the notion of exotic particles. Among them, tachyons stand out, hypothetical particles that, if they were to exist, could completely rewrite the laws of physics as we know them. These particles are theorized to travel faster than light, a concept that seems almost too bizarre to comprehend, yet their potential implications stretch far beyond mere curiosity. Tachyons, should they ever be detected, could challenge the foundations of Einstein's theory of relativity and even our fundamental understanding of causality. But tachyons are not the only exotic particles that intrigue physicists. Another tantalizing theoretical particle is the magnetic monopole, a singular magnetic charge that can exist as either north or south, unlike the familiar dipoles we encounter in everyday magnets. The very idea of a magnetic monopole pushes the boundaries of our understanding of electromagnetism and has intrigued physicists since it was first proposed. While certain grand unified theories suggest that magnetic monopoles should exist, they remain elusive, yet to be discovered any experiment. The mere possibility of these exotic particles reshapes how we think about atomic formation. If tachyons or magnetic monopoles do exist, their interactions with the fundamental forces of nature could open doors to entirely new realms of physics. Consider, for instance, the potential impact of magnetic monopoles on electromagnetic fields. If these monopoles existed, they could dramatically alter how electromagnetic forces behave, leading to new ways in which atoms and molecules bond, interact, and potentially form. These changes could lead to the discovery of new chemical reactions that are currently unimaginable, based on our current understanding of physics. Moreover, the existence of exotic particles like tachyons could unveil entirely new models of energy transfer and particle interactions, especially at the subatomic level. These revelations could offer a glimpse into the earliest moments of the universe, a time when conventional laws of physics may not have applied. In that primordial period, shortly after the Big Bang, the unification of forces and particles might have occurred under extreme conditions that exotic particles could help us better understand. This could reshape our comprehension of how atoms and molecules first formed in the aftermath of the Big Bang. However, as enticing as these possibilities are, studying atomic formation presents profound challenges. Atoms are incredibly small, so small in fact that studying them directly requires sophisticated, often mind-boggling tools. Particle accelerators such as the Large Hadron Collider, LHC, are among the most advanced scientific instruments ever created. Operating at energies that recreate conditions from a fraction of a second after the Big Bang, these devices allow researchers to probe the smallest building blocks of matter. Yet the sheer scale of such projects brings enormous financial and technical challenges. The LHC, for example, is not only incredibly expensive to build and maintain, but it also requires highly specialized expertise to operate. In addition to the technical difficulties, another significant barrier is the theoretical nature of much of the research. Many aspects of atomic formation, particularly those that extend beyond the standard model of particle physics, are speculative and difficult to test experimentally. The mysteries surrounding dark matter and dark energy, two elusive entities believed to have played a crucial role in the formation of atoms, remain largely unsolved. Researchers can only observe the indirect effects of these phenomena, such as their gravitational influence on visible matter, complicating efforts to develop concrete hypotheses. Yet, despite these obstacles, the potential for new theories about atoms and atomic interactions could lead to revolutionary shifts across multiple fields of science. For centuries, our understanding of atoms has driven breakthroughs in chemistry, physics, and technology. If fresh insights into atomic structure were to emerge, they could lead to profound advancements in diverse areas, from materials science to medicine. A new theory of atomic behavior could enhance our ability to predict atomic interactions with greater precision. This would undoubtedly have major implications for chemistry, especially in the development of new materials. Imagine discovering superconductors that work at room temperature, or materials that exhibit extraordinary hardness or flexibility, revolutionizing industries such as electronics, construction, and manufacturing. Moreover, the ability to precisely design drugs at the molecular level based on a more refined understanding of atomic behavior could transform medicine, enabling targeted treatments for diseases with unparalleled accuracy. In the field of physics, new atomic theories could offer fresh perspectives on fundamental forces and particles, potentially bridging the gap between quantum mechanics and general relativity. This unification could lead to breakthroughs in our understanding of the universe's most extreme environments, black holes, for instance, or the earliest moments after the Big Bang. Such a unified theory could change our conception of the universe's origins and its ultimate fate. Perhaps one of the most exciting applications of advanced atomic theory lies in the realm of technology. quantum computing is an area where new understandings of atomic behavior could drive major progress. Quantum computers harness the principles of quantum mechanics to process information in fundamentally different ways from classical computers. With deeper insights into atomic interactions and quantum states, we could unlock the full potential of quantum computing, enabling the solution of problems that are currently beyond the reach of today's technology. Moreover, a more detailed understanding of atomic processes could have groundbreaking implications for energy production. Take, for example, nuclear fusion, the process that powers the sun. By unlocking the secrets of fusion, we could develop sustainable and highly efficient fusion reactors here on Earth, providing a near-limitless, clean energy source that could radically transform the global energy landscape. As we reach the end of our exploration into the mysteries of atomic formation, we're left with more questions than answers. Atoms, the very building blocks of everything around us, have emerged from a vast cosmic void, leading us to question the origins of all that exists. Were atoms truly created from nothing, or are there unknown forces at play that we have yet to comprehend? These questions push us to examine not only the nature of the universe, but also the essence of existence itself. What do you think? Do you believe that atoms and everything we know were created from nothing? Or could there be other hidden forces shaping our universe in ways we have yet to discover? Share your thoughts in the comments below, and be sure to subscribe to our channel Starflux for more thought-provoking discussions. Thanks for watching.